Hi viewers, today again we are going to look at mean and variance of a Poisson distribution. Don't forget we just released a video under the mean and variance of normal distribution. So how do we obtain the mean and variance of a Poisson distribution? Poisson distribution is one of the discrete distributions that we have, and it has the probability mass function of PMF, that is probability mass function of P of x equal to exponential minus lambda x all over x factorial. So this x is a variable and it takes value from 0 to n. So it's a discrete random variable with these values 0 to n. So and the mean, which is this of any normal distribution, is given as this. So the mean of a Poisson distribution is given as lambda. So this is this. And the variance as well, which is this for normal distribution, for Poisson distribution is given as lambda as well. So how come about this? So we want to derive the mean and the variance of this Poisson distribution. If you recall that for any discrete distribution, the expectation or the mean is given as summation x function of x or p, which is the probability mass function of x. So your x, which is from 0 to n, from 0 to n. So this is for a discrete random variable. And yesterday we said for a continuous random variable, we use this as our expected value, which is integral negative infinity to plus infinity of x function of x with respect to the x. So this one is for continuous distribution, and while this is for discrete distribution. So the value here is from negative infinity to plus infinity, while this is from negative from 0 to any value, or is from a point from the negative side to any point of the infinity side. So that is why we call it discrete. It has a limited range. So we are going for this because a Poisson distribution is a discrete distribution. So this is the expectation or the expected value or the mean of any discrete distribution. Now, if our mean is given as this, then our P of x, which is the probability distribution of this Poisson distribution, is this. So we are going to insert it here, and we are going to have expected value of x equal to summation x equal to 0 to n of x, which is exponential minus lambda x all over x factorial. So this will be the expression for this when this distribution of a Poisson distribution is substituted. So now we want to find a way of getting our lambda. We know that our mean is lambda, so we are looking for a way to take out one lambda here, and if we are to do that, we express it in a way that we can get a special distribution whose sum is equal to 1 as well. As you know that the probability or the sum of any probability, the sum of any probability is 1, that is, either we are taking it from 0 to infinity, the sum must be equal to 1. So likewise for a continuous random variable, so the function of this with respect to ds must be equal to 1. So the sum of any discrete or continuous probabilities must be equal to 1. So we are going to apply the facts here. So what we are going to do now is, I want to make sure I cancel this x, and to do that, you know that x factorial, if you note that x factorial is equal to x into x minus 1 into x minus 2, then times, if you continue like that, the value of x will be reducing, which is 3 times 2 times 1. Just as if you have 5 factorial, so which is 5 times 4 times 3 times 2 times 1. So likewise the value of x as a variable, so it will be reducing. So we want to express this in this form in order to cancel this, and to do that we can easily say that our expected value of x is equal to, this will be summation of x from negative from 0 to n of x times exponential minus lambda, then lambda x all over. So this, we are going for this because we just need to cancel one x here. So we have x into x minus 1. So we can stop here because this x will take care of this x. So we can now say that this cancel this, and this is the same as summation x from 0 to n, so exponential minus lambda x all over x minus 1 factorial. So since we need one lambda, like I said, we need one lambda. So to bring out one lambda here, the way we express this, we are going to express this once again. So we can also have this as a summation x equal to 0 to n exponential minus lambda, then lambda x minus 1 times lambda raised to power 1. So you agree with me that if you multiply this and this, we are going to get this, that is, when we take the common base, which is x, and their power, if they are added, that is x minus 1 plus 1, which will cancel, and we are going to have this. So what I'm saying is, let's say we have we take the common base of lambda x minus 1 times lambda 1. So this will give us lambda x minus 1, then plus 1. So this will cancel this, we have a lambda x as well. So which is the same thing as this. So that means this is the same thing as this. I will have this as x minus 1 all raised to the power of this. So now we can take out this lambda. So to do that, we are going to have summation of this expected value of x equal to summation x from 0 to n of exponential minus. Don't forget, I'm taking this out, so I'm having lambda, so exponential this, then times lambda x minus 1 all over x minus 1 all factorial. So this work is already cool. We can just change this to a distribution. So let's take let our x minus 1 be equal to a. Let's use a. So if this is a, so it means our x, we can also find the value of x here. So our x will be equal to a plus 1, right? So what you want to do now is we want to substitute for a, which is this, and I want to substitute for x, which is this. So from here, if x is this and x is 0, we can also say that this, which is a plus 1, is equal to 0, and our a will be equal to what? Minus 1. So let's use this fact and get this distribution as expected value of x equal to lambda, then summation. So instead of writing this, we are writing this. So everything here will work for a equal to minus 1, then raised into n of exponential minus lambda x. So this one is this already, so which is a all over. So this is also a factorial. So this is just a distribution. Like I said, the sum of any distribution must be equal to 0. So if this is a particular distribution, which is a Poisson distribution, and if you take the sum, that is, by the time we are substituting for this value, when a is minus 1, you get it. When a is 0, when a is 1, when a is, so if you continue like that, by the time we sum up everything, the answer will be equal to 1. So it means this will change to 1, and we can now say therefore our expected value of x is equal to lambda times all this will be equal to 1, which is equal to 1. So that is the expected value or the mean of a Poisson distribution. So let's look at the variance of a Poisson distribution. How do we derive the variance? How do we derive the variance? So variance. We know that the variance of any distribution is given by this formula, or the formula which is moments about a point about the mean, which is this, and the expansion of this will give you expected value of, this is the second moment, which is this minus expected value of x all square. So provided that this is the population mean. So this has been proved, which is this. Now we want to find the expression for this. So expected value of x square is equal to summation x square. So x from 0 to n, then p of x. So just the same manner that we just use for this mean of a Poisson distribution, we apply the same logic here. But this will be somehow clumsy if we continue doing it as it is. So what we want to do now is, let's see if we can break this in the simplest form so that we can easily substitute the value, and it will make our work easier. What I think we can do here is we can say, or we can write this in this form, like x square can also be, or the expected value of x, or let's do it like this, our x square can also be written as x into x minus 1 then plus x. So this and this will give us if we multiply this and this, we are going to have x square minus this and this x, then plus x. So this can take care of this, and we're going to have x squared. So meaning this can be expressed as this. So we can now say this is equivalent to this, which is the identity. If this is equivalent to this, not an equation, it's just an identity. So we can now say the expected value of x squared is now expected value of x into x minus 1 plus x, and this will give you expected value of x into x minus 1 plus expected value of x. So we know this already, and this will be our mean that we just proved. So this is our mean, so we are putting it here. So this is what we want to look at now. So let's find this. Let's just call this equation asterisk so that we come back to it. And let's call this equation asterisk. So let's call this double asterisk and this one single asterisk. So we substitute for this. When we are done with this, we take the value here and we easily find our variance. So to do that now, let's find this. The expected value of x into x minus 1 is equal to, so using this fact as well, which is a summation, this. So we can have this x from 0 to n, then x into x minus 1, probability of x. So this the same as summation x from 0 to n, then x minus x into x minus 1. So the probability distribution of a Poisson, since we are working on Poisson, so that would be our p of x. We have exponential minus lambda, then lambda x all over x factorial. So now we are going to cancel this. And how do we get this? We can easily cancel this by expressing this in 2 times, that is x into x minus 1 into x minus 2. So we can have our value as this. So we can have a value from here. We can have a expected value of x into x minus 1, which is this. Is now our x, that is summation x equal to 0 to n of x into x minus 1, the exponential minus lambda, lambda x, then this. So we want to express this like x into x minus 1 into x minus 2. So we stop here because we need to cancel x into x minus 1, so which is this. So we stop at this factorial. So this will take care of this, and we're going to have our value to be what? Summation x equal to 0 of n, then exponential minus lambda, then lambda. So we can also take out lambda square here. So this is the same thing as lambda x minus 2, because if we multiply this and this, we're still going to get our lambda x. So everything divided by x minus 2 into factorial. So now let's take this lambda, let's take it to this side, and we're going to have our value to be lambda square summation x equal to 0 to n exponential minus lambda, the lambda x minus 2 all over x minus 2 factorial. So I've taken out this lambda, so this lambda is this, and that is what we need from this place. And this, we can let our x, just the method we used the other time, we can let our x minus 2 to be equal to, let's say we use a, so we can use anything we like. Let me use a as well. So here our x will be equal to a plus 2. So when this comes here, and if our x is 0, we can say this is equal to 0, which is equal to 0. So our A will be equal to minus 2. So let's substitute to this. We are going to have expected value of x into x minus 1 equal to lambda square summation x. So instead of writing x now, we are writing A equal to minus 2 into n of exponential minus lambda. This is our this. So which is our A. Then all over this is A factorial. So this, like I said, that this is a distribution, and the sum of any distribution must be equal to 1. That is one of the angles of a probability. So if this is equal to 1, we can now say that expected value of x, or implies that expected value of x into x minus 1 is equal to lambda square times 1, so which is equal to lambda square. So that is the value. So now we are taking this to this equation. So when we simplify this, we take it to this equation. So let's do that. So now from that place we have this. So we can now say our expected value of x squared, which is now expected value of x into x minus 1 plus x, which is expected value of x into x minus 1 plus expected value of x. So don't forget, this is our everything here is our value, which is lambda square. So lambda square, then plus, and this one is lambda, so that's the mean. So that means the value for this is this. So this is from our equation steric 2. So from equation steric 1 now, so we can find our variance. Therefore, our variance now, which is equal to expected value of x square minus expected value of x all square, so equal to this, which is this, and it's lambda square plus lambda, then minus this is also lambda all square, and by the time we do that, we have a lambda square, then plus lambda minus lambda square. So we can easily say this will take care of this, and the final answer will be what? Will be lambda. Therefore, the variance of the variable, which is the random variable, is also lambda. So we just prove that the variance is this, and the mean is also this for a Poisson distribution. So if you are new here, please help me to subscribe so that we get the latest video that will be dropped soon. So this is all what we have for today. Thank you so much, and love you all.